Hi, this is Steve Denenberg, and we are still working on work and energy. I want to look a little more closely at a little terminology that you already know, just to seat it well in your minds. We said that the total mechanical energy of a system is the kinetic energy plus the potential energy. And the potential energy can be the gravitational potential energy, the potential energy from gravity, and other kinds of potential energy, such as a spring's potential energy. And all of these are mechanical energy. Potential energies also are mechanical energy. It's not just the energy of motion that is the mechanical energy. So I saw a problem that confused me until I read it a little more clearly. You have to read these problems well. We'll talk about that later. And here's what it was. There was a plane that started 5 meters above the ground, and then it dipped down to the ground, and then it rose to 10 meters and continued like this. And there was a spring that was compressed and a mass attached to the spring ready to be launched. And you know what's going to happen. The mass launches, it comes out with a velocity v sub naught. It's going to head down, losing gravitational potential energy and gaining kinetic energy. And then it's going to go up the hill, regaining its gravitational potential energy and losing some kinetic energy. And it's going to be right here, and it's going to be heading out here with some velocity. We'll call this V2, and we'll call this V1. There was no friction. There was potential energy in the spring. And the question was, what happened to the gravitational potential energy of the object? And without reading the problem super carefully, I just looked at it and I said, it didn't change. There was nothing to change. But that's not true. The total mechanical energy did not change. But the gravitational potential energy increased. Because here it was mg times 5, and here's mg times 10. So keep those separate in your minds. Kinetic energy, gravitational potential energy, and potential energy from a spring. And if we want to beat this problem to death a little bit, we would say that the initial energy equals the final energy. And the initial energy was the potential energy in the spring plus the kinetic energy initial plus the gravitational potential energy initial. And that equals the potential energy final in the spring plus the kinetic energy final plus the gravitational potential energy final. Now this is okay, but they were just asking about the gravitational potential energy. Let's mention something that you will see called the work energy principle. The work energy principle states that the net work that you do on an object is the change in the object's kinetic energy. But we pretty much know that already. If you have a mass heading out this way at V1 and over a certain distance, a force is applied to the mass in the direction of its travel, then the net work done on the object equals force times distance, and you would add those joules, the same units as energy, to the energy that the object had to start, and that would equal the energy that the object has at the end. Or to be a little more organized with it, we would say that the final energy minus the initial energy equals the net work done on the object. So how does that help us? Well, there may be times when it helps a computation. Say you have a mass that's heading off in this direction at V1, and at some point in the future, the mass is now heading off in this direction at V2. Well, the change in kinetic energy of the object is 1/2 mv2 squared minus 1/2 mv1 squared. And the work energy principle tells us that it's possible that that much work was put into the object to get it to this new situation. Now you might be saying, well, but what about the change in direction? How did we do that? Nope, Work energy principle talks about energy, which is a scalar and not a vector. This can work, even if the directions are changing. Or, let's say you have a mass moving along at v sub naught, and it runs into a brick wall and stops against the wall. Well, you know it started out with 1/2 mv sub naught squared of energy, kinetic energy, and now it's got none. So you know that whatever happened, the wall did this much work on the mass to get it to stop. Now we have a couple things to do before we quit. We have to talk about power. How is power different from energy and work? Let's go back to our storehouse with the 3 shelves, and you have those boxes on the middle shelf, and you want your worker to bring them up to the top. Well, when he came to do the job, Bill got the job done. But on the day that Tom came to do the work, Tom got it done in half the time. Tom was much faster getting the job done. Tom was able to deliver more power. Power is work done per unit time. So if you get all those boxes to the top shelf, you're doing work. And if you do it in a short amount of time, you're doing it with a lot of power. So let's say Bill did 10,000 joules of work in 100 seconds. The power that Bill was delivering to his job was 10,000 joules divided by 100 seconds, and that's 100 joules per second, and we call those watts. After physicist and inventor James Watt, who was refining the steam engine in the mid-1700s. Now what did Tom do? Tom did the same 10,000 joules of work, but it only took him 20 seconds. So we divide 10,000 joules by 20 seconds, and he developed 500 watts of power. So once again, since this is energy put out per unit time, it's joules, which is energy, divided by seconds, which is the units of time, and that's watts, W4 watts. If you do a lot of work in very little time, that's when you're putting out a lot of power. So now are we ready to understand what a horsepower is? That's how we talk about how strong our cars are. How much power do they put out? How fast can the powerful engine deliver energy to my car so it can get from 0 to 60 in only 5 seconds? Most cars can get from 0 to 60 as the engine puts work, energy, into the car. The car speeds up, it has more velocity, it has more energy. But if the engine is powerful with a lot of horsepower, then that energy is being delivered in a short period of time, and you can get from 0 to 60 in only 5 seconds. Well, James Watt was trying to quantify for the public that he talked to how much power his steam engine would put out. But if you're talking about joules, people can't connect with it. So he thought he would quantify how much power a typical horse could put out. Actually, it was a specific kind of horse that he was thinking about. But his estimate was that a horse could raise a 550-pound weight 1 foot in 1 second. So it would take that horse 10 seconds to raise a 550-pound weight 10 feet. It's doing a certain amount of work, force times distance, in a certain amount of time. So if he told someone that his new steam engine would put out so many joules per second, they would look at him like he's crazy. But if he said the machine would do the work of 5 horses, they could immediately connect with that. So to put it into units that we typically work with, this would be 165 pounds being raised 1 meter every second, or 75 kilograms being raised 1 meter every second. And in the Earth's gravitational field, a mass of 75 kilograms means the horse is providing a force of 750 newtons for 1 meter every second, and that's 750 joules per second, or 750 watts. He could have told him that a horse puts out 750 watts. Then, to apply a little 8th grade algebra to this, since power is how fast you're doing work, we can rearrange that equation and say that work equals power times time. So if some process, some machine, some windmill, some engine is putting out P power for a certain amount of time, we can compute how much work it has done. So if a generator is putting out 100 watts and it runs for an hour, the generator applied 360,000 joules of work to whatever was the recipient of that power. And now here's a teaser for a later video, more 8th grade algebra. If you can do W work in T seconds, you are delivering W over T power, as we've said a million times. Now, if you deliver a certain force over a certain distance, you've done that much work. So replacing W in this equation, we can say that if you give a certain force over a certain distance in a certain amount of time, you're delivering that much power. Well, distance over time is velocity. So let's rewrite it again. Let's say we have velocity for this. So we will say, if you can deliver a certain force to something that's traveling with velocity v, you are developing a certain amount of power. And just as we saw a minute ago, that work equals power delivered times the time it's delivered, if you deliver a force to something that's moving with a velocity v for a certain amount of time, then that's the amount of work. That's the amount of energy you have added to the target of your force. And after we've talked about angular momentum and ellipses and Kepler's laws and hyperbolic orbits, I'll show you how you can use this to escape attacking aliens. And moving on from that enigmatic statement, a special treat. I will dispel the mystery around a formula that we take for granted. We say that the kinetic energy of a moving particle is 1/2 mv squared. We memorize that, we use it all over the place. But why is it 1/2 mv squared? Well, the work energy principle says that the work done on an object equals the change in its kinetic energy. So if we're saying that the kinetic energy of a mass m moving at velocity v is 1/2 mv squared, why don't we start from first principles and see how much energy we must deliver to a mass that is at rest in order to get it to move with velocity v. Okay, so you have a mass, and you apply a force to the mass. And the mass starts to accelerate. It's faster and faster, constant force, constant acceleration. In time t, the mass moves a distance of 1/2 a t squared, where its acceleration we know from the force delivered. F equals ma, and the acceleration equals the force divided by the mass. This is all simple stuff that we saw in our very first video. Now, how much work did we deliver to that mass? Well, work equals the applied force times the distance that the object traveled while it was under the influence of the force. And there's no cosine theta here because the displacement direction is the same as the direction of the force. Well, we know what the distance is. That's 1/2 at squared. And we know what the force is. The force is ma. So the work applied to the mass equals force times distance, ma times 1/2 at squared. Let's simplify that. That's 1/2 times m times a squared t squared. Well, if a body starts from rest and accelerates with a constant acceleration a, then its velocity at time t equals a times t. If it undergoes an acceleration of 3 meters per second for 2 seconds, it's going to have a velocity of 6 meters per second. So let's take v equals at and substitute it in here. The work done is 1/2 m at squared, and that's 1/2 m v squared. And that's how we know that the kinetic energy of a mass m traveling at velocity v is 1/2 mv squared, because it takes that much work to bring the body from rest to velocity v. Thank you for your attention. If you have any questions or comments or suggestions, my contact information is right here or in the description below. See you next time.